Alright guys. So I gave examples of metrics, and now we can see that a bunch of them are equivalent. So the idea is this. So if I have a sequence xn, and that's a sequence in the set M, and then if I endow M with the distance d, so you might have the situation that xn converges under the distance d to x. But if I change the metric, I might give another metric, and xn might not go under the metric rho to the point x. It might not be a convergent sequence, or does not converge to the same point under a different metric. Okay, so then we make the following definition. We will say that metrics md and m rho are equivalent if a sequence xn converges to under d to x, this happens if and only if xn will converge to x under the metric rho. So you see what I'm saying? Two metrics are equivalent if they generate the same convergent sequences. So we have the following fact. There is a proposition about following metrics. So we can say that if rho of xy is defined as a function f applied to the distance xy, where f from 0 infinity to 0 infinity is a real valued function that satisfies so first thing, it satisfies that the function, I already mentioned it here, so I'm rehashing that the function is always bigger than 0, and it's equal to 0 if and only if t is 0. The second condition is that the derivative is bigger than 0. And the third condition is that the second derivative is less than 0 when t is 0 infinity. You can change this condition by just replacing it by, let's say, first derivative is a decreasing function. In other words, if the graph of f is the right graph, the type that we call the graph of an external method function. Okay? So that's y equals f graph. Okay? Then we can say that d and rho are equivalent on M. So here I'm saying that suppose we are given a distance d. The distance d acts on points in M. And then I can modify the distance by the external method, and I'm generating an equivalent metric. Soon we will see equivalent metric implies homeomorphic topology or identical topology. Okay, so the reason this is true is very simple. Proof. So again, I'm using advanced tools, some tools that properly we haven't justified in analysis, but you know of continuous functions, you know of differential functions, and you know if those concepts are made rigorous, this idea is then clear. So the proof is, we can say that f is continuous, thus if xn goes under the metric d to x, that means that distance of xn to x goes to 0, and that implies that if I apply the continuous function under distance xn and x, that distance will, because this point is converging to 0, so therefore applying a continuous function, now this function will have to converge to f of 0 by continuity, which is by assumption I equal to 0. So what this shows in particular is that as soon as I have a convergent sequence under the metric D, it will converge under the metric rho. You see what this is saying? So what I'm saying is xn going to x under D implies that xn goes to the same x under the metric rho. Okay? Now we need the other direction. So assume that xn goes to x under the metric rho. Now rho of xn to x is simply the function f applied to the distance of xn to x. Now because the function its derivative is positive, the function is invertible and the inverse is continuous. So the implication is that if I apply f inverse to rho of xn x, that is the same thing as the distance from xn to x, and so we have that distance of xn to x equals to the inverse rho xn x, and this is because the inverse is a continuous function, this goes into f inverse of 0, but f inverse of 0 is 0. Okay, so again, I used a bunch of assumptions that need much more justification, but you see the function is differentiable and the derivative is positive. It means it's increasing, it means it's invertible, and the inverse is continuous, so it's very trivially true that the external method generates equivalent metrics. So then without too much trouble, I can conclude as in this example. Okay? That's what I can easily conclude. So suppose that I have distance between x, y is simply the absolute value of x minus y on R. Okay? Then if I take and define pxy or rho xy equal to, say, root of absolute value of x minus y, right? So that's a new metric generated by the external method, or if I define sigma of xy to equal maybe absolute value of x minus y over 1 plus x minus y, or I define tau of xy equal to maybe ln of absolute value x minus y plus 1, or if I take phi of xy and define it to be something weird like root of ln of absolute value of x plus y, x minus y, sorry. Divided by 1 plus root of ln x minus y plus 1. So this ugly looking thing are all equivalent to d on R. Okay, so all those functions trivially, because you see all of them are generated by composing with a function of this form. They all are generated by the external method. They all generate the same convergent sequences. And when we talk about open and closed sets, or if you talk about it when you study topology, that means that they generate the same structure. All right, so here's another question I have. So question: must equivalent metrics generate the same Cauchy sequences? What do you think? Okay, so you understood what equivalent metrics do. They take convergent sequences to convergent sequences. And there is a one-to-one correspondence. One convergent sequence under D corresponds to the same sequence converging under ρ to the same point. Must the sequence respect Cauchy sequences? Sorry, must the distance respect Cauchy sequences? Yes?
Okay, maybe no, because just because it converges doesn't mean it's Cauchy.
No, careful. If it converges, it means it's Cauchy.
That the other way around.
So the other way around, Cauchy does not mean convergent, right? So just logically, you see that there is no necessity. It has to respect convergent sequences. It can do anything it wants with Cauchy. Poor Cauchy. So here is what we can have as an example. So let MD be equal to simply the interval from 0 to infinity together with the absolute value. Okay? And let's pick our favorite sequence. So let's pick, so this is this absolute value. So consider the sequence 1 over n. Okay? So this 1 over n is Cauchy under D. In other words, what I'm saying is that if you take the distance between 1 over n and 1 over m, this is going to 0 as n and m go to infinity, right? In other words, as you delete terms, the absolute value between 1 over n and 1 over m, distance is going to be small. And now we can take rho to be a different metric. So take rho of xy to be absolute value of 1 over x minus 1 over y. Okay, this rho is equivalent to d. Here is why it's equivalent. So one direction is if I take xn under d to x, then by continuity of g of t equal to 1 over t, so 1 over t is continuous on this set, we would have that 1 over xn goes under the distance d to 1 over x, which is the same as saying that xn goes under the metric rho to x. Right? So you see by continuity, what is this metric doing? It's really composing those points with a continuous function and then measuring the distance. Okay? And this is the internal method. It just happens that I compose the distance with a continuous function. And similarly, on the other hand, if I have, let's say, Zn converging under the metric rho to Z, that is equivalent to saying that 1 over Zn converges under the regular absolute value metric to 1 over Z. Okay? I just use the same function, so they are equivalent. You see, they generate the same Cauchy sequences. Sorry, not the same Cauchy sequences, by no means. They generate the same convergent sequences. And this is not completely, that's the same as 1 over Zn going to that, to 1 over Z, and so that will imply that 1 over 1 of Zn goes under the metric d to 1 over 1 of Z by continuity. Okay, so they're equivalent metrics. That's the main point here. But 1 over n is not Cauchy. So it is not Cauchy under rho. And the reason for that is I can take rho of 1 over n to 1 over m. This is simply the absolute value of n minus m. And that doesn't cluster. Okay? So of course the reason this works is that notice that 1 over n isn't convergent. in MD. That's important, right? The reason it worked is that 1 over n, we eliminated the point 0. So it is not convergent. Yet, it is Cauchy. And this metric is equivalent, but it did not respect this Cauchy sequence. So, yes?
So I understand, so the reason that metric rho worked is because you eliminated 0.
Yes, otherwise it will not even define a metric. Or if you translate to complex analysis, it will, but then infinity is actually a point that is available to us. Okay? So this metric is Cauchy if you look at it on the sphere. So the integers, they approach infinity, and infinity is 1 point. So they gather around infinity. Okay? So it's always context specific. So so now in terms of equivalence in norm vector spaces. Okay, equivalence of norms. So for that, let M be equal to, say, Rn. And then we have the following. Then, if I take distance 1 between a vector x and y to be the magnitude of x minus y using the 1 norm, and I take d2 from x to y to be the regular Euclidean norm. Okay, so you understand what this means, right? That means you square each component and you take the square root of the sum. And the infinity norm here, what you do is you take the absolute value of each coordinate and you take the maximum or the supreme. Okay? They are all equivalent. So why are they all equivalent? Well, observe. So we have on one hand, we have that the infinity norm is always less than or equal to the 2 norm. Do you see why, right? So here, the infinity norm is like taking the square and taking the square root of one number. Here you are squaring each number, adding them up, and then taking the square root. So this is obviously no smaller. Okay? And then by repeated application of triangle inequality, you should see that this is like the hypotenuse of a triangle, and it is less than or equal to the sum of the lengths of the sides. Okay, so and the sum of the lengths of the sides will then be the 1 norm. So this is less than or equal to the 1 norm. Okay, so that means what? That means that if I have a convergent sequences in R2, it will force the sequence to converge in the infinity norm, because you see this goes to 0, forces this guys to go to 0. And then if it converges in the 1 norm, it forces it to converge in the 2 norm and in the infinity norm, right? So on the other hand, we have the following relationship. So we know that if I take the one norm, this will be less than or equal to n times the infinity norm. Okay? Do you see? Do I need to explain? Do you see why this is true? So what is the one norm? I add up all the coordinates. So I take the absolute value of x1, x2, x3 and add them up. Okay? Now what is this doing? It's picking the biggest coordinate. So if I add all the absolute values of the coordinates, clearly it's not going to be as big as if I multiply the biggest coordinate by n. Because here I'm adding the biggest coordinate to itself, and here I'm just adding all of them. Okay, so this is one relationship, so there is dominated convergence, you see? So if it converges under the infinity norm, then this guy goes to 0. So if you have xn going to x under the infinity norm, so this is like 0 times n, and that forces the one norm to go to 0. Okay, so this together with this shows the equivalence of the 1 in infinity norm. You follow me, guys? You see, this means that if it converges if a sequence converges in the one norm, it converges in the infinity norm. Now this inequality tells me convergence in the infinity norm converges in the one norm. Okay? And then we have other relations. So we have this relationship and we have this relationship. So the one norm is less than or equal to the square root of n times the 2 norm. And this is Cauchy-Schwarz. You see what I do? So a vector, so should I justify it? So here, right? So the one norm, so if I have, let's say, if I have a vector, so let u equal to x minus y, okay? So what is u? U will be equal to u1, u2, u sub n, okay? Now, what is the one norm of u? So if I look at u, the one norm, what is that? That's simply absolute value of u1 plus absolute value of u2 plus absolute value of u sub n, which is equal to the dot product of the vector 1, 1, 1 with absolute value u1, absolute value u2, absolute value u sub n. Okay? So there's a dot product, right? Now the dot product, now this is a positive dot product by Cauchy-Schwarz. This is simply less than or equal to the 2 norm of the vector 1 times the 2 norm of the vector u1 all the way to un. Okay? You see this? So what is this guy? This guy is just add up 1 and take the square root, so that's just equal to the square root of n. Time this is just the norm of u in the two metric. Yes? So that's where this comes from. Okay, so that's why this inequality is Cauchy-Schwarz. And now that means that if it converges under the 2 norm, it forces convergence under the 1 norm. And with the other inequality, you can see a sequence converges in the 2 norm if and only if it converges in the 1 norm. As it happens, even showing this is too much energy. Once you know a little bit more about finite dimensional spaces, you can show that on a finite dimensional space, every norm is equivalent to any other norm. Okay, and this is used when you study analysis of manifolds. They don't even bother mentioning which distance you can use, and in many books you just quickly just jump from one norm to another. Sometimes taking the supremum is the easiest approach, okay, because that's easiest to deal with. Sometimes it's the 1 norm, and sometimes it's the 2 norm. The theorems, whatever you use, the theorems are equivalent. So if you have derivatives that you established using this distance, it will be the same as using the Euclidean distance. It doesn't matter.
Professor, a question.
Yeah.
Could you say, use Archimedean property and say that maybe n is just any constant that makes the infinity norm big enough than the 1 norm?
Well, the thing is about Archimedean property, you first specify the number, and for that number you have to pick a lever. But here n is ubiquitous, n is the dimension of the space. Okay, so this is telling you, this is in fact is a strong equivalence. Not only is it preserving convergent sequences, it in fact will preserve Cauchy sequences as well. Because you see, if it clusters together under the 2 norm, that means it will cluster together under the 1 norm. That you can just substitute sequence xn and xm, and this going to 0 implies this going to 0. So this is stronger, it preserves Cauchy sequences as well. This is known as strong equivalence. Okay? And Archimedean property, again, right, you can think about it, but you see this n is not dependent on the particular x or y that we pick. Archimedean property tells you pick a positive, so this, forget about, so pick a positive b and a positive a. If you multiply a by big enough number, it will be bigger than b. That's the Archimedean property. So, yeah. So you can look at this thing, clearly if you multiply the particular x minus y norm 2 by a particular number, it will be bigger. But will it always, but maybe there is no upper bound on how big I have to select the coefficient. Okay, I hope it is understandable what I'm saying. Right, so this root of n is the dimension, it's coming from this n here. It's the dimension of the space. All right. So, last thing I want to say about equivalent metrics, and then we can move on, is we can now define so if definition given metric space MD and rho, we can define a metric on the Cartesian product m cross n. So you know what Cartesian product means. It means that it's pairs of numbers. So if it's R and R, that's how you get R2. Okay? And the definition will be simply, you can define the metric to be, for example, maybe I'll define it as distance, let's say distance 1 from AX to BY to be equal to the sum of the distances of the coordinates. So it would be distance from A to B, it's like the 1 norm, plus rho of xy. Okay, so what I'm saying is, again, in the space Mn, I have one point, and that one point is A, B, and I have another point, and this is xy. And how do I measure the distance? Okay, so I can simulate the one metric distance, that would be the one where I just use, for the first coordinate I use the d metric, and for the second coordinate I use the rho metric that is defined on n. I can also define it as maybe d2, which would be a distance from AX to, sorry, let me say the point here is AX, and this point here is BY. Now that makes sense, yes? So X is an element of n, and Y is an element of n. A is an element of m, and B is an element of m. So distance from AX to BY. Now this will be the 2 metric. Can you tell me what should I write here? If it's the 2 metric, what do I do?
Squaring into the square.
Yeah, so I take the distance from AB, and I square it, and I add to it the distance from x, y, squaring it, and then I take the square root, and that will generate a metric. Or maybe the infinity. That will simply be, in this case, there's only 2 points, so I can use maximum. Maximum of the distances from A to B, and rho x to y. Okay, that will generate equivalent metrics. They're equivalent. So this is just simulating what we do for Euclidean spaces, but you just have a different distance on the shoot. I mean, it's easy to show. I mean, really, triangle inequality, all those properties, they fall as soon as you know that they hold for the rho metric. Okay, so you understand. You would understand if you needed to prove that those are metrics, you would not have problems, right? The hardest part is triangle inequality, and that we already worked with holders, so nothing worse can happen to us, right?